This is Solve It for Kids.
Hello, my amazing and curious friends. My name is Jennifer, the Dean of all things STEM and STEAM, and this is Solve It for Kids, the science podcast that gives kids and families a peek inside the real world of scientists, engineers, and experts as they solve problems in their jobs using creativity, cooperation, and critical thinking. And now please welcome to the show my podcast partner, Galactic Space Geek, Jeff Gagne.
Hello, Jennifer, and hello, listeners. This week's Best Of gets us into topics that we don't normally think about, and you are going to find them fascinating.
Absolutely. This one is so much fun. I really love this Best Of. So what episodes are we learning from today?
The best of learning about our universe.
Ooh, the best of learning about our universe.
Yes!
This is going to be so amazing. So you're going to hear clips from episode 192, How Do You Study the Smallest Things with Dr. Katie Grimm. Episode 170, What Would Happen If We Didn't Have Magnets? With Dr. Dario Arena, which is a great question.
Such a cool guy.
And we're going back in time to one of our earlier episodes, episode 63, How Do Scientists Listen to Black Holes? With Dr. Eric Thrain.
This is one you're going to listen to more than once.
Absolutely. This is a really, really fun episode. So we hope you guys enjoy them. Take a listen.
How do you study the smallest things?
How do you study the smallest things? This is going to be a really fun episode. Who is our guest today, Jeff?
Our guest today is Dr. Katie Grimm. She is an associate professor of physics at Cal State University East Bay, and her research is done at CERN.
Welcome to the show, Dr. Katie.
Thank you. It's great to be here. Thank you.
Well, we are so excited to have you, of course, because you do physics, which I love physics. Physics is one of my favorite sciences, and you do such cool stuff. But what I want to know is, when you were a kid, did you ever imagine that you would be smashing things at CERN one day and learning all about physics?
No, I had no idea that this was a thing you could do.
I was going to be a little concerned if that was a yes.
Right. No, I guess when I was little, I didn't know what I wanted to be, but I was always into like space. I was always into like sci-fi. I liked Wrinkle in Time and Star Trek and stuff. And I had good math teachers. I always thought math was fun. Then later, I guess when I was going to college, I was thinking I would do earthquakes. I grew up in California. Earthquakes. So I started taking some classes for that at school. Okay. Let me tell you, it is so complicated.
Really?
Yes. But as I was studying earthquakes, I had to take, regular physics, not geophysics, but regular physics. I really liked how they break everything down to really see like what's fundamentally happening and all stuff, everything around us. And then I got into particle physics, which is like really what's inside the atom, what are the smallest things? And then you're down to like super simple stuff. Like there's only 17 particles in the whole universe, compared to like what's going on with the Earth's crust, which is so complicated. I was like, okay.
I think my head's about to
once
explode.
You get down to that level, it really is.
Yeah. I mean,
really at the sci-fi
17 particles? That's it?
That's it in the whole universe. That's how you make every single thing in the universe, is with the little combinations of those seven.
Gosh.
Imagine if you only had 17 Legos, but you could make the whole universe.
Okay, well, this might be our shortest episode ever. Oh, wait, we just had a particle physicist tell us, it's simple.
Exactly.
Okay, so when you thought it was going to be earthquakes and you started taking some of those classes,
Did you accidentally wander into a particle physics class? How did that switch happen?
Almost. You have to take a lot of like the building blocks, the fundamental physics classes. And so
Okay.
as I was doing that, I was also taking some geology stuff, which I do like. But then I did hear about this particle physics, particle astrophysics. So I took that too. And it really grabbed me. It's like really has a sci-fi element. Like once you get down to things that are that small, it's not like our normal world. And so then I was like, this is basically like A Wrinkle in Time, but it's real science. So
Oh my
Excellent.
gosh. So can you explain kind of what you mean by that? Like, what
Right,
do you
yeah.
mean that it doesn't work at the same level when down there?
Right. Once you get into really, really small stuff, then there's quantum mechanics, which means that people noticed when they were measuring these things that things don't quite exist in space in the same way as objects in
Wow.
normal everyday life. You try to measure
Okay.
something that's really small and it moves, or it's not
Oh,
Oh.
measured enough times and you realize it's not really there at all. Maybe it's just sort of a chance. You have a chance of seeing something. Everything is like
wow.
something might be there. You have to roll a dice, and then depending on what you get on the dice, it's there or it's not there. It's like all you say, it's ruled by probability at those small scales.
Whoa.
this
Yeah.
totally
And stuff can
sounds
go through
science
walls.
fiction.
Yeah.
Yes.
Yeah.
That's complicated stuff, and I think it's great.
I was just going to ask.
Yeah.
So, is that sort of weirdness about this science what drew you to it?
Yeah, I think it is. I think like once you get down to those levels and then every new thing you discover, like, what? Is this really how it works? It appears it is how it works.
Okay.
Now I'm
Okay.
measuring it just to be sure.
Yes, exactly. Okay. So I want to back up a little bit, and I want just for some of our younger listeners or people who don't, know what makes up an atom. Can you kind of talk us through what makes up an atom and then the parts that you're talking about that are really, really small?
Yeah, for sure. So everything is made of atoms. And just to be clear, I know like a lot of times you learn about cells, right? All living
Yes.
things are made out of cells. And this is even inside of that. So smaller than cells, everything is made of atoms. And even not living things like the air and plastic and metal, everything is made of atoms.
Okay.
And every atom has a nucleus. And so like the middle part, and the middle
Right.
part is made up of protons and neutrons.
Yes.
And depending on how many protons there are, you get a different material. So that's like really what
Ah.
distinguishes different materials is how many protons
Okay.
are in there. And then you can go deeper than that. You say, what's inside the proton? And now we know that inside the proton, there are quarks.
Ah.
The quarks have super funny names. There are 6 different quarks, and they're called up, down, strange, charm, top, and bottom. Sometimes like the last ones
Okay.
are called truth and beauty. So I heard that they named them that because they didn't really think they were real. And then they found out they were real and they were stuck with the names.
Oh, there you go.
Careful
we
when you
got
name
those.
something.
So if you're a kid, you're probably saying, well, what's inside those quarks? Because kids always ask that whenever I talk to
Yes.
them about this. And that is the right question to ask. And right
Okay.
now, we don't think there's anything inside them. We think that those are the smallest things, that if you try to break apart a
Oh.
quark, there's nothing. That's it. That's a fundamental part of the universe that can't be broken into something else. So there we say, okay, we made it. We found the smallest, we started at an animal, and we went into cells, we went into the atoms, we went inside the atoms, inside the nucleus, and we got to quarks, and we think that that's it. That's the smallest thing.
Okay, now I want to be that annoying kid and ask, haven't we thought that we found the smallest thing before, but we didn't? So what makes us
Yeah.
think that quarks are now the end of it, the smallest?
Yes, that is exactly the question you should ask. It's a little bit hard, the answers. I will say that there are many, many people looking for what's inside of quarks.
Ah.
there are people on it. I'm not specifically looking at that, but one of the reasons that we think that there's nothing inside of quarks is there's like a way that you can add energy to things that are made of other stuff that makes them kind of ring, or you say there's an excited state, you put some energy in and things inside can bounce around. And we've tried to do that with quarks, then nothing happens. There's no you made that into like an excited state of the particle. So that's one hint that maybe there's not, maybe we really have made it to the bottom.
Yeah.
All right.
Okay. So now that we know that they exist, how do you study these tiny little quarks? I know you work at a pretty amazing place called CERN. Can you tell us a little bit about that?
Yeah, CERN is an amazing place. It's a big lab. It's in Switzerland, and they have something nobody else has this, or at least they have got the biggest one.
Yes.
They've got the largest collider of particles. So this is a huge tunnel, and inside of the tunnel, you accelerate protons. So these tiny, tiny things inside of atoms, you put them into a beam, and using magnets, you turn them so they're going in a circle, and you get them going really fast in two different directions. And then you smash them together. In some ways, it's like not that sophisticated an idea to figure out what's inside something. You just smash it, and then you look. But it turns out that by doing that, we can measure really carefully. And this is like, a lot of people working on how to measure what happens when you smash them together. You look at all the stuff that comes out, and then that tells you about the quarks. It tells you also, and this is where I think it gets really interesting, that moment when you smash together the protons, because you've got so much like speed coming together. You think of like two really fast things, two baseballs hitting each other with tons of energy.
Right.
That energy of the two protons puts you in like a different space that is similar to the early universe. So like at the beginning of the universe.
Oh, wow.
All of the stuff that we know now, we think was really, really close together. And so had a lot of energy really in a small space. And that's what we're creating when we smash together those two protons. So besides seeing what's inside the protons, we're also making new particles. And they're particles that only existed in the early universe when we had more energy in a small place. So we're learning about how do those quarks, how can they reconfigure and make other particles besides protons? How can we create other particles besides quarks? There are some other fundamental particles that we've made.
Wow.
And how do these things interact and then make everything we know in the universe?
What would happen if we didn't have magnets?
What would happen if we didn't have magnets? I'm guessing this is something pretty big. Who is our guest today, Jeff, that's going to explain all this to us?
Our guest today is the expert on the topic, Dr. Dario Arena, and he is Associate Professor of none other than physics at the University of South Florida.
Welcome to the show, Dr. Dario.
Hello. Thank you so much for having me here. I'm very happy to be on Solve It for Kids.
Well, we are excited to have you. We're going to talk about all things magnetic, which is going to be a really cool episode, I think. So I have to ask, were you that kid that played with magnets?
Yes, I was the kid who played with magnets.
Yes.
And I wanted one of those giant magnets that the Roadrunner had, that the Coyote had, that he used to catch the Roadrunner with. I really wanted one of those.
Oh, yeah. Those, I think we all did as kids, yes.
Oh, yeah,
I like
exactly.
That. So I do need to ask now, what was the biggest or strongest magnet you had when you were a child?
Yeah.
When I was a kid, the magnets were, I'm old enough to be sort of an earlier generation of magnets where they had that U shape, and those were not that strong.
No, they
so
weren't.
now we have much better magnets that are shaped like a bar.
Right.
And those are much, much stronger magnets. And you can do all sorts of fun things with them. You can even levitate trains with those kinds of magnets.
Yes. Yes,
Whoa.
that's very cool. So
Yeah.
how did your love of magnets as a kid turn into a career down the road?
Well, the love of magnets sort of led me to physics
Okay.
Okay.
because I wanted to understand how magnets work.
Yeah.
And so to understand how magnets work, you have to understand some physics. And so that's kind of led me to the path of trying to figure out the things that I should study, which turned out to be physics. And then eventually when I finished my PhD, my doctorate, I got a job using X-rays to look at magnets.
Wow.
Yeah, so that was very cool. That was a really cool job. And then that led to my working on magnetic materials and sort of understanding how they're put together and their properties using this really cool instrument called a synchrotron.
Wow.
Yeah, so that was
All
a lot
right.
of fun.
That sounds
We have
fun.
got some cool stuff to talk about.
Yeah.
So I want to start at the beginning. Can you describe for us in sort of basic terms how a magnet works?
So to talk about how a magnet works, I got to talk about a property called angular momentum. And that's
Okay.
a big word.
Okay.
Angular momentum is kind of like the mass of an object, but it's a little bit different. So the mass of an object is related to a property that we call inertia. Basically, how difficult is it to move that object?
Yep.
Angular momentum, we kind of we use a term called spin, which is a little inexact, but you can kind of think of it that way. So an example of angular momentum is a bicycle.
Oh, yeah.
Okay.
And a bicycle, if you just are not pedaling and you try to sit on a bike, you'll tip over.
Yes.
Oh, yeah.
Yes. You can't
But if
sit on
you-
a bike if you're not moving.
Yeah.
Exactly. It doesn't work. You got to pedal. You got to have those wheels spinning. When the wheels spin, they produce a property called angular momentum. And that angular momentum keeps you balanced.
Oh,
So that is, and how
Wow.
magnets work is essentially pulling together all the angular momentum of the electrons in a material in a way that they stabilize the direction of those little tiny angular momenta of the individual magnets.
I
So
did
you
not
can-
know this.
I
This
have
is
never
very
heard it
cool.
explained this
No.
way.
Very,
Okay.
very cool. So it relies on this sort of really basic property of electrons called angular momentum, the way that many other properties rely on the mass of objects.
Okay. So how does this relate to what we know about magnets, how it attracts other magnetic objects or repels them? How does that angular momentum play into that?
So everything has angular momentum.
Okay.
The trick is you can kind of the trick or the problem, depending on how you want to look at it, is that most materials, all of that angular momentum cancels out. So think about a bicycle wheel. If a bicycle wheel is spinning in one direction, it's going to have angular momentum in one direction. If you have a second bicycle wheel that's spinning the opposite way, it's going to have an angular momentum as well, and they cancel out.
Okay, got it. Okay.
And in most materials that we experience every day, that's what happens to the angular momentum of the electrons. They just cancel out.
Okay.
But
All right.
there are some special materials that we call magnets
Right.
where they don't entirely cancel out. So now I have more, let's use left and right.
Okay.
I have more angular momentum pointing, let's say, to the left than it
Okay.
does to the right. So
Okay.
now I've got a net angular momentum pointing to the left. And that angular momentum, if you study the math a little bit, produces a magnetic field that then can be
Wow.
used to attract objects.
No
Wow.
kidding.
I'm
Okay.
I'm kind of blown away here. Wow.
I really
I
have
just
never
thought
heard
they're
it.
little magnets, That's so
Yes.
cool.
Yeah, they
fixed
are
up
little
to the
magnets all the
fridge.
way down to the level of electrons.
Right. But I mean, I didn't really think about how the electrons move in the field that they create is how all of it works.
Yeah.
Okay.
So
I'm
So that
impressed.
leads me. You were mentioning earlier that we now have bar-shaped magnets instead of those U's. And if you use one end of the bar, it will attract something. And if you use the other end of the bar, it may repulse something.
If that other object is magnetic,
Okay.
is sort of intrinsically magnetic. So if you have
Okay.
one of these bar magnets, they have two sides to them. We typically call them north and south.
Right.
And if you sort of, most people use magnets to like stick stuff on their fridge, right?
Right. Exactly.
yeah.
My
So if
fridge
you
is
take-
covered with magnets.
Exactly. Yeah, that's what we all do. We put pictures of our kids, our dogs, notes to remember to pick up the milk, all sorts of things. Chores, list of chores go up there too.
Yep.
But when you're using a magnet to stick something to a fridge, it doesn't matter which side you're using, north or south, because the material underneath the fridge, it has electrons that respond to the field that's produced by that north or south pole of the magnet.
Okay.
So it's going to produce an attractive force either way. However, if you bring a magnet, a north pole, let's say 2 bar magnets, and you put their north poles together, you're going to feel a force that is repulsive, that wants to push the 2 objects away.
Okay.
If you have a north pole next to a south pole, now you get an attractive force, and it wants to pull the 2 objects together. So opposites attract, right?
Yes.
So north and south will attract, north and north will repel, south and south will repel.
Okay. So you're saying that every material has types of magnetic qualities in it. It's just not necessarily magnetic as we would think about it. Is that correct?
Yeah, that is correct. And I told you a tiny, tiny lie.
Okay.
And I'm sorry about that. I said that most materials are not magnetic, and that is almost true. There's this property of all materials called diamagnetism, which is another big giant word. But that is something that occurs when you stick an object in a really, really strong magnetic field. And then you can actually make that object very, very, very slightly magnetic. And you can do some cool things with that. So, for example, there are some videos on the web that you can find called The Levitating Frog.
Oh my God.
Where you can actually put a little tiny frog in a droplet of water, and you put it in a big magnetic field, and the frog is happy because the water and the frog, because most of us animals are mostly made up of water, has this little diamagnetic contribution. And the diamagnetism is like that North Pole with the North Pole or the South Pole with the South Pole. It's a repulsive force.
Right.
So you can now get that little frog in its bubble of water to float in midair.
How do scientists listen to black holes?
Oh, now I understand. How do scientists listen to black holes? This is going to be fabulous. Who is our guest, Jeff?
That is right. How you listen to black holes. You heard that right, everybody. And today we are going to be talking with Dr. Eric Thrane, astrophysicist, university professor, and gravitational wave scientist, who is going to tell us about one of the most amazing discoveries that has happened in the last 100 years in science.
Ooh, welcome to the show, Dr. Eric.
Thank you so much for having me. It's a pleasure to be here.
Oh, so I think this is one of our coolest episodes and we haven't even started. So you work with gravitational waves. So the big question is, what are gravitational waves?
Indeed. So it all begins with Einstein's theory of gravity, which is called general relativity. And according to Einstein, space and time are combined into something called space-time. Right. And you can visualize it like a rubber sheet. That rubber sheet has things like planets and stars on it. And when you put them on the rubber sheet, the sheet warps, it sags.
Sure.
And that warping is the presence of gravity. That's what the force of gravity is. It is essentially the warping of space-time. So for example, if you want to think about the motion of the moon around the Earth, imagine putting a bowling ball on a rubber sheet. The bowling ball is the Earth. It causes the sheet to sag. And then you take a little marble, that represents the moon, and you roll it on this sagging rubber sheet, and it will go in a little circle around the bowling ball representing the Earth. That's the picture that Einstein gave us of how gravity works. And the rubber sheet, that's the warped space-time. And gravity, according to Einstein, is just the motion of these marbles and balls, planets and stars, on a warped sheet of space-time. So far, so good?
That's the coolest. I know, right? That's the coolest explanation ever. Now I understand. That's so cool.
All right, but we got to work up to
the rubber sheet made it much more understandable.
Yes.
Cool. So this is the picture we've had of how gravity works for about 100 years. And once you have this picture of general relativity in your mind, there are some pretty weird consequences. One consequence is that you can get holes in your fabric sheet. You can get punctures. So if someone comes by and they put a really, really big bowling ball on your stretchy sheet and they pile mass onto it and make it bigger and bigger, what will happen? The sheet will sag more and more, right?
Yes.
Right.
Eventually, if that sheet sags too much, it will get a hole in it, a puncture, a rip in the fabric of space-time. And that rip, that puncture is called a black hole. This is a region of space-time that is so stretched, so distorted that no light can escape from it. And we think of it as a hole in the fabric of space-time.
That doesn't sound good. I mean, right? I'm just thinking, okay, real, like we've watched all of these TV shows and movies, and you know that space-time ripping is bad, right? So
it sounds bad, but we're very safe here on Earth. The black holes like to stay where they are and mind their own business. So they're fascinating objects, a little bit scary when you first learn about them, but like many things in science, as Marie Curie said, they're not to be feared, only to be understood.
Okay.
So we've done two concepts. We're working our way up to gravitational waves, which was this is our selling point, right?
Yes.
We did the fabric sheet of space-time, and now we have these black holes, these rips in the fabric of space-time. And now finally we have what we need to make gravitational waves. If you have two black holes, two rips in the fabric of space-time, and you take them and you smash them together, this is a little bit like taking two bowling balls on your fabric sheet and smashing them together. What will happen? The answer is it's a little bit like taking a pebble and throwing it into the center of a pond. Little waves or ripples emanate outward from the splash, and you'll see them spreading in a circular pattern outward as they get to the edge of the lake. The same thing happens when two black holes smash into each other. They make waves, but these waves aren't water waves. They're ripples in the very fabric of space-time itself. And these waves travel to us all the way at Earth, maybe 1.3 billion years later in some cases. And they cause tiny, almost unimaginably small stretching in the fabric of our space-time here on Earth. And I have a challenge now for our listeners, if I may.
Oh, yes. Please.
So if you're sitting, please stand up, and I'm going to have a gravitational wave come through you. Are you ready? Everyone standing?
Okay, we're standing.
All right. So everyone's standing up. I want you to stretch up as high as you can and suck in your tummies and put your head up as high as you can. And then slink back down, bulge yourself out at the middle, and put your arms out wide. That's what it's like to be stretched by a gravitational wave passing right through your tummy. It makes you first taller and a little bit skinnier, and then it stretches you the other way and it makes you slightly wider and shorter, and it oscillates back and forth. Short and thin, tall and wider, short and thinner, taller and wider. And it does this, we think all the time, these gravitational waves are passing through us, stretching us just very, very slightly. But they're so small, you can't tell that they're passing through you. You can't feel it. So what we need to do is make special instruments in order to detect these very small ripples in the fabric of space-time.
Okay, so I'm following so far. I understand.
Yes.
So we obviously now have that special equipment, I'm guessing, which is part of why it's been 100 years since Einstein first described this effect, but we haven't seen it until now.
The story of how gravitational waves were detected is an amazing story about human perseverance and the ability of people to take on some of the most challenging scientific problems and engineering problems that the universe can throw at us. So as you said, Einstein pointed out about 100 years ago this idea of gravitational waves. And for a long time, people debated whether they were purely mathematical, something that is not a real effect that you can feel, but just something with numbers. Later, scientists agreed that they must be real and set about to building detectors that could measure them. But it took thousands of scientists working over many decades and hundreds of millions of dollars of investment from governments to build technology that would allow this to happen. In particular, the invention and perfection of lasers, devices that could make very pure beams of light, was an essential ingredient in order to detect gravitational waves. Can I tell you how we did it?
Yes, absolutely.
Please.
So the first observatory to measure gravitational waves is called LIGO. And LIGO stands for Laser Interferometer Gravitational Wave Observatory. And it works like this. Shall we do another audience participation for this one?
Yes,
Definitely.
I think this is great. Jeff and I are up for it.
Put your left hand up in the air, stick it straight up, and put your right hand out to the side so that you make an L with your arms, okay? These two arms represent the 4-kilometer long arms of the LIGO detector. That is, for our American audience, a few miles, right? I can't do this.
Okay.
And what you're going to do is when you're in your tummy, that's where the laser is. And it sends a light beam down these two arms.
Okay.
And the laser light beam bounces off a mirror at the end of your two arms. So the mirror is on your fingertips on each arm. And the light bounces off that mirror and it comes back to your heart where the laser was. And when the two light beams come back, we time how long did it take. You can put your arms down now, by the way, listeners. We time how long did it take to go down each arm. Now, if a gravitational wave is stretching you, it's pulling your one arm up and squishing that the arm you're raising up is getting longer and the arm that you're holding out to the side is getting shorter. But then the next moment, the arm you're holding up is getting shorter and the arm that you're holding out to the side is getting longer. And by timing how long the light takes to go down each of these two arms, we were able to work out that a gravitational wave had passed through our detector. And what's really neat is that we can say more than just that a gravitational wave passed through the detector. We can say something about what created it.
So many amazing guests on this show. We love it so much. If you are like me at all, you are right now thinking of other episodes that may be favorites that were completely off the wall topics that made you say, wow, I never really thought about that, but the next time I see it, I am totally going to be more engaged with that stuff. These episodes really hit that note for me.
Yes, absolutely. They were so much fun and they were so unique, Jeff, based on some of the other people that we've seen. This is amazing. So if you liked these episodes and you want to leave us a comment and let us know, you can tag us on social media. We are at KidsSolve at Facebook, X, and Instagram. And now we have a big announcement about the podcast. We would like to thank you all for being amazing listeners. Jeff and I have celebrated 4 years of this weekly podcast.
Yes.
We are now going to make it every other weekly. So for the rest of the year and all of our next seasons, we're going to be every other Tuesday. But don't worry, we're still going to bring you amazing guests with really intriguing and fun episodes and topics. And don't forget, you can always suggest a topic to us or a person that could be on our show. So feel free to reach out to us through our website, solveitforkids.com, because we'd love to have you on the show. But this is going to be so much fun going forward. Right, Jeff?
Absolutely. Season 9 is coming up.
Yep.
We have been doing this, like you said, for 4 solid years, every week. We're moving to every other, but that just leaves us more room to engage with us. We want to talk more about these amazing science topics, engineering topics, and these wonderful guests that share all of their incredible jobs. All these people love so much what they do. And Jennifer and I already have a whole list of great guests lined up for our brand new season, which you will hear starting live again next week. Until then, you'll hear Jen and Jeff on Solve It for Kids.